No, devi andare a cercare Dave YouTube channel. Certo che potrei farlo anch'io, sono d'accordo anch'io, Allora. Sì. E poi c'è dal vivo. Adesso, Dio santo santissimo, come farò? Sì, come farò a condividere lo schermo? Però dovrebbe essere già che tu lo vedi, no? Cazzolina.
Beh, cattura schermo macOS.
Lo vedi? No, cattura schermo.
Io sono entrato. Ma dal vivo non vedo niente.
Però dovrebbe essere già che tu lo vedi.
Però mi devi iscrivere al canale, forse.
No. È tutto nero, si sente l'audio ma non si vede il video.
Impostazioni lì su basso a destra.
No. È tutto nero, si sente l'audio ma non si vede il video. No, Skype.
Io sempre niente.
Aspetta. Aspetta. Ha una latenza di circa 30 secondi. L'abbiamo misurata con i tecnici. Vediamo se
C'è
arriva.
una bandina qui adesso. No, non c'è. Questo qui è quello che si sta arrivando. Sì, prima che non terzi per questo.
Sì, non ti serve. Faccio un attacco anti-alimentazione del computer. Non credo sia necessaria, però...
E mi incomodo se io resto qui. Nicola deve restare qui l'altra volta.
Guarda, secondo me tu puoi stare qui davanti perché hai fatto questo. Questo mi sta facendo preoccupare. Magari ammazzo l'audio qui.
O poi se sono 50 minuti anziché 45 non penso che...
Tutti hanno sforato,
Ok.
non ti devi preoccupare, dai.
Voglio c'è da cambiare per un'ora. Questo cazzo di colpo di tosse secca ogni tanto.
Quando io feci il talk c'era un pezzo di talk per la presentazione per quando c'era un mega passaggio a associati e qui c'era praticamente tutti quelli candidati potenziali e fai talk a tutti per vedere. E cazzo, io avevo esattamente in quel periodo lì un abbassamento di voce, non un abbassamento, proprio un azzeramento di voce e andai un pochino in panico perché dissi cavolo combina. Ok, adesso arriviamo a toccare questa cosa. Allora, penso che non è necessario che lui stia di sopra.
No.
E quindi noi possiamo tranquillamente...
Però aspetta, lui è collegato a questo.
Sì, ma credo che il cavo HDMI dovrebbe darci un minimo di flessibilità, no? Perché il software per streamare sul canale YouTube, che è la cosa più facile per condividere con persone che stanno fuori, ne abbiamo installato i tecnici e di fatto gira sul mio computer. Poi adesso, dalla prossima volta forse non ancora, ma da febbraio io mi tolgo un po' dalle scatole della gestione di questo e lo faccio fare a quelli che entrano come RTTA, perché io ho fatto quel che dovevo fare, no? Non è che potevo fare. E quindi chiederò a uno di loro di mettere sul software, poi useranno il mio, poi useranno quello il loro, fine. E qui hai la tua cosina.
Ottimo. Conviene forse metterlo già sulla coda.
Allora, sai cosa? Volevo far partire una via registrazione
Giusto.
e quindi e poi lancio. Non lo faccio alle 5:30, lo faccio un pochino.
Sì.
Ho fatto sta roba.
Tutto l'orologio allora?
C'era anche la nostra contenta, cioè.
Beh, ma anche perché cioè, è stato effettivamente un passaggio davvero sottile per certi versi è infuocato da precedenti,
Secondo me io sono zigogolato, tu non hai detto.
sì.
Ciao, voglio dire mandare il segnale.
Io sono Stefania.
Mi ha sentito proprio.
È un nome così più e dopo la questione via matematica si è trovato a fare la punto perché ho detto vabbè voglio vedere comunque si è riuscito le risorse però c'era la sinistra la sinistra però quindi comunque sia in interesse qualcosa che va oltre interessante basta se mi dicono sì e questi mi fanno così arrotonda lo stick cazzo per ora non metti dove posso vivere parlo con questa ragazza dice no ciao ciao
Mi presento, sono Paolo Giannini, piacere di conoscerti.
usa, cioè, si va più avanti. No, non si esiste. Noi stiamo dando per scontato che funzioni sto coso qua. Quello che non capisco è
Beh, scusa, cioè sì, Paolo.
sì, sembra che funzioni. Sì, sì. Quindi, non so sempre a 0 quello del Mac.
No, prima che faccia fischio.
Però quello che posso fare è vedere se qualcuno mi ha scritto mail
abbassare queste due qua? No.
Non c'è la possibilità di controllare. È come se ci fossero delle cose predefinite, cioè è così, ci sono queste cose predefinite e quello che puoi fare è semplicemente cliccare sulle cose predefinite. Sto dicendo un attimo. Adesso mettiamo le slide e vediamo un attimo. Dai, va benissimo così, no? Sembra che vada benissimo. Io però ti modifico una cosa.
Vai, 23.
Sì.
So che la serie fosse quella del 22, quindi...
È vero, però avevo messo ogni...
Giustamente.
Aspettiamo ancora un pochino che... Ci dovrebbe esserci Marcello, dovrebbe esserci... non mi ricordo, no, un po' di gente. Comunque una settantina di persone avevano biddato. Quindi... altrimenti devo pagare davvero, cioè devo chiamare tutto il dipartimento per...
mangiare.
Sì. Però c'è un po' di gente...
Da noi cioè, in questi giorni è abbastanza vuoto.
So just very quickly, hi guys, thank you to be here. This is the first seminar of the new year, and it's let me say a pleasure for me to have people working on artificial intelligence beyond the department of electronics and computer science. This is the first researcher that we have here. Not next week, but the week after, another guy is not exactly a guy anyway. It is Riccardo Zecchina from Bocconi University. So our intention is to have people working in the field outside computer science. So again, Andrea Manzoni from the Department of Mathematics. Thank you to be here. You can start.
Thank you, Nicola. Happy New Year to you all. And of course, thank you for being here and for giving me the opportunity of presenting sort of trip in, say, between deep learning and scientific computing. This is a 2.5 years trip, and I would like to highlight some challenges and perspectives in disordered modeling, in particular of physical systems. Before starting, some acknowledgements to the people that essentially contributed to the material I'm going to present to Stefania Fresca, so a researcher at the Mathematics Department, Nicola Raves Franco, currently postdoc in our department, and then some people from the Civil Engineering Department, Giorgio Govat, researcher there, Paolo Conti, PhD student under my co-supervision and the supervision of Professor Attilio Frangi, now director of the Civil Engineering Department, Paolo Zunino, who is also here, full professor of numerical analysis at Mathematics Department, and some people that are from University of Twente, Mengo Guo, and from EPFL Lausanne, Jan Staven, actually vice director of EPFL. And last but not least, Federico, who was previously with us in the department, and Alfio, that for sure you all know very well. Now, why essentially talking about, say, scientific computing and deep learning? Well, of course, many applications from, say, applied sciences and engineering are required to perform complex simulation of complex multi-scale systems. You may very often face large-scale numerical approximation problems. For the sake of accuracy, you want to deal with very fine computational meshes. You have to deal with dynamics that are usually quite expensive to simulate or also challenging to forecast. Some instances, some applications are reported in the slides. You may face problems, for instance, that tend to sort of chaotic limit in cardiac electrophysiology. You have complex behavior and complex patterns of flows in blood dynamics, that is a cerebral aneurysm. You have also very tiny structures. This is an example of a microelectromechanical systems that, of course, is going to, say, under some loading, say, it moves, and then you want to characterize the mechanical displacement, and last but not least, turbulence. But we could for sure, say, continue with a very long list of examples. So in all these cases, can we design fast, possibly multi-scale or multi-physics methods that reproduce coherently the system dynamics? The numerical simulation is not the final goal very often. Maybe it's only the first goal, because very often you may be interested in facing contexts like being able to simulate in real time a given system for multiple scenarios. You want to perform data simulation, you want to quantify uncertainty, you want also to build so-called predictive digital twins. So by relying on, say, traditional high fidelity or full order models is essentially unfeasible from a computational point of view. And this is the reason why the disordered models, provided they are accurate and efficient, must be called into play. So independently of the fact that you are interested, for instance, in supporting clinical decision to perform structural health monitoring, few more examples, well, physics-based models are computationally expensive. So the question that immediately arises is, well, can AI help? And in particular, how can AI help? In the last 2 or 3 years, of course, a big, say, emerging topic is the one related with scientific machine learning. This is the cover of a report from the US DOE, so the Office of Sciences, essentially focusing on, say, scientific machine learning, trying to define scientific machine learning as a sort of collection of tools, both from machine learning and scientific computing, so at the interface, at the intersection. And the goal is to develop new methods for scalable, domain-aware, robust, reliable, and interpretable learning and data analysis against all, say, keywords that you share, say, every day. Everything will be critical in driving the next wave that I wrote of data-driven scientific discovery. So somehow we are at the interface, at the intersection between the data-driven methods and physics-based models. This is a personal viewpoint of some of the goals that arise in, say, facing complex physical models. Physical models, I will spend some words about this, will be, say, based on differential equations, partial differential equations, ordinary differential equations. I don't want to be boring on this, but somehow these are some of the goals that we need to face. So, first of all, numerical simulation. We want to build reduced order models or surrogate models to be efficient enough. Of course, accurate as well. We have also to learn very often physical laws based on data. This is the classical task of data simulation, of forecasting, but also of model discovery. Going on, we want also to say some words about how those models are going to approximate the solutions of the problems we are facing. How, for instance, we can take into account approximation theory to design in a good, possibly optimal way, the neural network architectures we will introduce. Last but not least, we have algorithmic augmentation. There are several trends nowadays performing, for instance, closure models or subscale modeling through, say, deep learning algorithms and not only deep learning. And last but not least, uncertainty quantification regarding, say, parameter estimation, uncertainty propagation, and also multi-fidelity methods. Depending on time, I will maybe spend some words about also multi-fidelity methods. So there are several enabling methodologies. So the field is extremely active, in my opinion, in these last, say, few years. Regarding numerical simulation, I'm going to focus on two of those pieces. The first is numerical simulation. Well, starting from bottom to top, so you can decide to inject less and less physics and more, say, information from data. We can start from reduced order models where we are going to consider, say, linear subspaces where we are going to approximate the solution of our problems, and we still have to face the solution of mathematical problems. We can be less and less intrusive in this kind of tasks. I'm going to focus on deep learning-based reduced order models and showing how to exploit essentially deep learning to perform the construction of those reduced order models. A very recent trend is the one related with the so-called physics-informed neural networks. I'm going not to focus on this, but there are several papers, say, appearing in these last 5 years. Somehow you want to introduce some inductive biases related to the physical model in the neural network architectures, and then going, say, up to, say, Gaussian processes or neural network regression, so very input-output, say, emulators. And last but not least, we have also to face the task of learning maybe the, say, physical system we are going to simulate. We have to estimate some parameters, for instance, through the usual MCMC methods. We can also identify the nonlinear dynamics, still relying on regression methods, or, say, moving to a sort of discovery of the latent continuous dynamics, for instance, using neural networks. Of course, this is just a list of some instances of methods that fall under this class. I'm going to focus on some of these methods. Basic ingredients: neural networks, and in particular, say, on the scene will appear deep feedforward neural networks, LSTM, autoencoders, and deep convolution autoencoders. Depending on the time, I'm going to cover some of these parts. So how this can be translated to the need of performing reduced order modeling. A reduced order model essentially is a, say, as the words say, a reduced representation, a low order representation of a complex, high fidelity, usually large scale problem. And the three tasks I'm going to focus on this presentation are, first of all, the solution approximations. We want to provide the solution of the whole system we are going to simulate. the velocity field of a fluid, the velocity and pressure for a fluid, the displacement field for a structure, and so on. Not just a scalar output, not just a single quantity of interest, but the whole solution field. This is a key point. If time allows, I'm going to focus on model discovery, somehow the use of sparse identification of nonlinear dynamics in this context, and last but not least, on, say, multi-fidelity methods to perform output approximation. In the case you are just interested to quantify the behavior of some quantities. I don't know, the lift coefficients in a fluid, the dry coefficient, some output quantities of interest. And of course we could also continue on the other side, but I've decided just to focus on these three aspects. The question, say, shared by all these blocks is, can scientific machine learning enhance reduced order modeling? Of course, we know how to perform the construction of reduced order models. I'm going to revise very briefly in a few minutes how, say, traditionally, numerical analysis provides, say, solutions to construct reduced order models, but sooner or later you need to face some limitations, you need to overcome some limitations that these traditional techniques say pose, and deep learning indeed has been in this couple of years, say, a key tool enabling us to, say, overcome those computational bottlenecks in several applications. So the first section is devoted to the say, construction of deep learning based reduced order models. Before, say, entering into the realm of deep learning, what is a reduced order model? Well, sooner or later, no matter if you are playing with finite elements, finite volumes, to take your best, say, numerical approximation strategy, you need to, say, solve huge, large-scale linear systems. If you linearize a system that is nonlinear, well, sooner or later you have, say, many linear systems to be solved. And this is also due, for instance, to the presence of parameters. Mu denotes parameters, parameters related to the physics or the geometry. I don't know, the Reynolds number for a fluid or some loading conditions on a structure, you can think to your best problem, to your best application. Very often the scale of this system to be solved is very large, millions or billions of equations in, say, millions or billions of unknowns. Well, a reduced order model somehow exploits the fact that the presence of those parameters make the solution set not just, say, a sparse set of points in a very high dimensional space. Now, the parameterization induces, say, a sort of structure, of manifold structure of the solution of this problem. And we want to, first of all, sample those manifolds. We want to compute some, say, high fidelity solution to some properly sampled parameter values. And we want to use them to, say, to build a sort of approximation space to, say, give the solution for any new unseen, say, parameter instances of parameter values. So now, sort of offline, online paradigm, a sort of training testing paradigm already is underlying the construction of classical reduced order models. So we start by computing offline some snapshots, so we still need to rely on the, say, classical high fidelity solver, but once we have computed them, well, the first basic strategy, the so-called reduced basis method, well, gives us the possibility to look for the new solutions for any new unseen parameter values in the subspace generated by those, say, possibly few snapshots computed offline. So rather than, say, looking for points on the black manifold, I'm going to look for points on the red manifold, being this red manifold lying on this hyperplane. This is, of course, a cartoon to give the idea. So there are two questions, essentially. How to generate the approximations? Well, we can look, say, for approximations in this linear subspace. How to combine linearly those basis functions? Well, we need to set, say, a new problem to be solved online. And this is an option that the reduced basis method, say, gives us the possibility to approximate the original solutions by a linear combination of, say, basis functions. This is a basis, a matrix collecting all the basis functions. Everything is at the algebraic, say, level for simplicity. And then what we somehow impose is a sort of orthogonality on the space that is generating our approximations. At the end of the day, if you start from a linear problem, that is, say, characterized by a very high dimension, well, you end up with a, say, low-dimensional problem that is still linear, with a matrix that is, say, depending on the, say, arrays, the original matrix and this basis matrix, and the same happens on the right-hand side. So, of course, for linear, stationary problems, the technique is extremely, say, well-defined and well, say, studied from a mathematical point of view. If you now pass to non-linear, time-dependent problems, well, the technique is still working, so that the building blocks are still the same as before. You need to explore somehow this set of solutions. You need to assume that the new approximation is a linear combination of basis functions, and then you need to project. At the end of the day, you end up with a dynamical system that is of small dimension, and small means order of 10, hundreds possibly, say starting from millions or billions of equations. But from a dynamical system, you reach a dynamical system that is still, say, nonlinear, and it has to be solved once again. So I've compressed the dimension, but at the end of the day, I still have a dimension, a dynamical system to be solved. This is more or less, say, in 5 minutes, say, sort of 20, 25 years of, say, reduced order modeling following, say, the reduced basis method. This is not the only, say, available technique, but this is one that, say, among the others has been exploited very, very much. How to, just a couple of slides, how to build that space? Well, we go back to classical tools in numerical linear algebra. We exploit the singular value decomposition, essentially as per the principal component analysis does, say, for data science. I collect all the data in a snapshot matrix. I perform the singular value decomposition of that matrix, and the POD basis will be, say, the set of the first modes, of the first, say, columns of the singular vectors, say, of the original data. Why? Well, say, the Schmidt-Cardian theorem says that among all the possible, say, n-dimensional bases, well, the ones that has been obtained, say, using this trick is the one that minimizes the reconstruction error between the original snapshots and their projections onto, say, an n-dimensional space. And last but not least, this result tells also that the error that we are, say, introducing by replacing the original data with those, say, POD approximation is related to the scales that you are discarding, to the sum of the singular values that you are not including in your system. So everything, say, works. The field variables can be computed quickly, but, well, assembling these dynamical systems can be even more expensive than, say, solving it, and this is the first computational bottleneck. But often problems are not reducible, because if I look at the decay of the singular values, maybe there are cases in which those singular values do not decay at all, or decay in a very poor way. So this means that the reduced dimension n of the reduced base approximation is not so small, or is not as small as desired. And this, of course, is a strong limitation to this problem. This is an example, a motivating example coming from cardiac electrophysiology. You have just 3 parameters. So mu1 is the time at which you deliver the second stimulus on the tissue. This is a small portion of tissue. You have the radius of the circular region where you deliver the stimulus, and some properties related with the tissue. So just 3 parameters on a, say, nonlinear reaction diffusion problem that is unsteady. There's time, of course, and you have also the coupling between, say, the tissue scale with the cellular scale. So this is already a multi-scale problem. Well, gives you very different scenarios, completely different scenarios, just playing with 3 parameters on this 2-dimensional, say, square domain. If I look at the singular values, well, I realize that, well, they decay not very fast, and in particular, if I fix some threshold, say, to the accuracy I want, well, I very soon reach, hundreds of modes, hundreds of basis functions. And even if I play with some local reduced basis, I can perform k-means clustering to, say, build, say, not just a global space, but local spaces, while also in this case, the dimension in this case is 200. So the relative error is under any, say, desired accuracy. We want to reach errors at the level 10 to the minus 2, well, but the price we need to pay is the size that is not so small, not so reduced of the reduced basis space. So what we need are better reduced order models. And this is what essentially led us to, say, look for a sort of a generalization of POD, and an autoencoder somehow can be seen as a nonlinear generalization of proper orthogonal decomposition, because already, say, the compression and the decompression stages of POD, of course, through a linear transformation in the POD case, well, resemble what an autoencoder indeed does. If fed with, say, found snapshots, we need to look for a later representation in terms of a very low dimensional representation. Of course, we need to learn, in this case, the maps that bring us to, say, the high dimensional to the low dimensional representation and back. But this is just, say, a part of the story. Because if you start from high fidelity data, these are, say, the finite element of solution that you have computed. Well, also introducing convolutional layers, you can reach, say, a very low dimensional representation of your data. So this is the encoder and the decoder part in blue here. So I will somehow need to get the reconstructed, say, solutions as close as possible to the original one. But remember, we still have to solve a problem for different times and for different parameter values. So somehow the reduced problem that before was originated by projecting, say, the full order system onto the reduced dynamics, well, now is given by a deep feed-forward neural network that connects, say, time, that in this case is seen as an additional parameter, but we will further elaborate on this aspect later on, and the parameters to, say, the low-dimensional representation. So independently of the fact that you train, say, the two architectures separately, or say, in a one, say, shot, I would say, this is what at the end of the day, is a deep learning based reduced order model, at least the way we have, say, conceived it. During the online testing stage, once I have learned all the, say, networks here, well, I will be able to, say, evaluate very cheaply, inexpensively, say, the first network giving for new parameter, unseen parameter, and a given time, say, the latent representation, and then I will go back to reconstruct, say, the original solution. So the question is it working? Well, I skipped some details related with all the training stage. Yes, it's working, and it's working very well. We start from, say, a two-dimensional problem, and then now applications will follow a sort of increasing order of complexity. A problem that takes, say, 4 minutes to be solved by the finite elements, take less than a second to be solved with a deep learning-based reduced order model. Also in cases where a traditional, say, POD-based ROM took, say, 15 or 10 seconds. And parameters here are related with the position where, say, a lack of conductivity in this tissue is somehow, say, placed. So this is the same problem of before, and you are somehow modeling the effect of a scar tissue that can be, say, placed everywhere in the domain. Similar problem, but now with, say, more complicated pattern. You are releasing now a second stimulus to the tissue in different positions, say, on a vertical line at the middle of the domain, so that there's just a single parameter. In this case, also, say, the DL-ROM takes a couple of seconds to provide a solutions that also, say, is very accurate compared to the high fidelity simulation. The question is how to choose the reduced dimension n. Well, if on the one hand using POD somehow can exploit the fact that the singular values decay tells us how many modes can we consider, well, in this case this is less clear. And we have tried, in collaboration with Nicola Rares Franco, that is a PhD student, and Paolo Zunino, that is also here, well, we have tried to extend, and these are the last two, say, technical slides. We have tried to extend, say, how, say, the so-called Kolmogorov, with somehow, say, the capability of linear subspaces to approximate, say, solution sets can be read in a sort of nonlinear analog. So if this is the quantity that from a theoretical point of view tells us, well, the problem is reducible or not, well, we have, say, extended, well, we have exploited this notion that had been already introduced in the literature back to the 70s, and to try to understand how an optimal compression can be performed. So how the minimal latent dimension can be related to, say, quantities that are, say, depending on the problem. And some results are this. Well, somehow the number of parameters is a key quantity that allows us to, say, relate the dimension of the latent space and quantities that are related with the problem. Restricting, for instance, to, say, second order elliptic partial differential equations, we always start from, say, basic problems to then generalize everything. Well, in this case, we can bound, for instance, the latent dimension by some quantity that scales linearly in the number of parameters, and that is given by 2 times p or even p in some cases. P is the number of physical parameters or geometrical parameters that you have. Okay. And last but not least, we have also tried to, say, perform a sort of complexity analysis in order to link, say, the two sources of errors that we have, a sort of reconstruction errors because we are encoding and decoding the solutions, and then the parametric error because for new parameters we are solving the problem at new location in the parameter space. Those two contributions to the total error combine, and we can somehow, say, state a connection between, say, a desired tolerance that you want to the sum of these two errors, and, say, the number of weights, the number of layers that you have in the autoencoder or in the deep feed-forward neural network. And more recently, we have also extended this kind of results to convolutional neural networks, so autoencoders that also include convolutional networks. So this is to say that also from a mathematical point of view, say, using deep learning algorithms in these, say, kind of disorder models actually, say, make the very, say, interesting and also very complex questions, say, to arise, and we have tried to face some of these aspects. Now, the dimension we have just seen here or here can be cut very small. We can query the solution at the testing time for any new time we want. We no longer need to solve the whole dynamics till that time, because the time here is a parameter, so we can query the DL realm for any desired time, so we no longer need to solve the dynamical system till that time, but we still, say, require an expensive training stage if the data that are, say, used here feature a very large dimension. Because if you think that those data are just, say, finite element solutions featuring millions of dimensions, and then you want to reach a reduction to very, say, few dimensions, of course, here you need to, say, to compress a lot. And this is the second, say, method we have introduced last year. Somehow we use, say, a preliminary dimensionality reduction through POD, no matter if the number of POD modes to be included is large. But these, I don't know, 1,000 POD modes will be, say, in any case less than the million of unknowns that you had at the beginning. And then applying, say, the DL-ROM idea to, say, the solutions projected onto, say, the POD space as, say, allowed us to solve, say, even more complex problems than the previous ones. So the idea is the same. We still have two contributions in the loss to be minimized, the reconstruction error and the sort of, say, compatibility error between, say, the outcome of this feed-forward neural network and, say, the encoder. But in this way, we have been able to somehow overcome the limitations posed by the dimension of the full-order model. And the training times now have been, say, cut substantially. Other, say, key features behind this, say, methodology, sort of pre-training, we have also seen how, say, simpler model can be trained first in order to initialize the training of the final architecture we want for, say, learning the final task we are interested to, and also randomized SVD and not just pure SVD to even reduce computational times. Now there's a sort of gallery of, say, applications, because we started from simple problems, and then we saw that since everything is essentially data-driven, where those data are generated numerically, there's no longer physics involved into the DL-ROM. Well, we really have been able to say, solve completely different problems. We started by structures, for instance, and then we moved to cardiac electrophysiology. Those are results obtained, say, in collaboration with the team of the HIART project led by Alfio in these years. So just to give an idea, this is a ventricle and this is an atrium, a problem that takes 3 hours, 3 hours and a half with a full order model, say, finite elements, would take less than a second to be solved on a GPU when this POD-DL-ROM is used. And now parameters are related once again with the position where those stimuli are released. So we are really able to reach even faster than real-time solutions, because an RB takes more or less 1 second. And we are able to reproduce what happens in a ventricle or in an atrium in less than a second. This is fluid dynamics. So we move to, say, vector valued problems with more than one field, velocity and pressure, starting from, say, traditional benchmarks like the flow past a cylinder. Then we moved, for instance, to, say, the approximation of both velocity and pressure, and then other lift coefficients. All those comparisons are between, say, finite elements and POD-DL-ROM, and the accuracy is, as you can see, very good. This is what happens in a cerebral aneurysm. Once again, these are Navier-Stokes equations in a 3-dimensional domain. Well, this is the full order model, finite elements, and this is essentially the same results, but obtained with a speed up that is order of 10 to the 5. And the comparison between, say, the flow in the, say, in the central part of the aneurysm essentially is very good as well. And why to stop to fluids and not to involve also fluid structure interaction, for instance? Well, also to perform the simulation of complex fluid structure interaction problems. There is this elastic beam that is going to move on the back of this fixed rigid block. Well, also in those cases, the results are impressive, let's say. And more recently, thanks to a collaboration with the civil engineering department, the group of Professor Attilio Frangi, we also applied all these, say, techniques to the simulation of the mechanical behavior for the time being, all the mechanics, and these are micromirrors at the order of the microns that, say, under some, say, loads, of course, start oscillating. And just to give an idea, manufacturers are interested to characterize the so-called frequency response surface for, say, values of the amplitude and the frequency of the loading you have on the structure. You want to understand which is the maximum angle. And here you can see also the nonlinear behavior that can be either stiffening or hardening in this kind of material. Well, you can characterize, say, millions of instances in a couple of minutes. Okay. And this is just for, say, the sake of even more applications are another kind of maps. Now, I hope that, say, I have convinced you that, say, using deep learning is essentially a key enabling technique for, say, performing real-time simulation in very different domains, also facing quite complex applications. Now, in this part, I've included a couple of slides or sort of outlook. Because, of course, now we have considered so far in these slides, consider data as columns, and columns that have been maybe reshaped to allow, say, convolutional layers to be applied. But we would like to solve problems on very general domains. Think about the ventricle or the atrium you have seen before. And so we have tried to extend the idea, say, of before to a sort of machine forward version of these neural networks. Somehow trying to say to tackle problems that are defined on very general domains, and in particular exploiting the topology of the mesh. Somehow the fact that some vertices are close or not in the mesh can give us very, say, good insight of the fact that maybe the values related to the weights and the neurons that will process them, well, can be maybe turned off or on. And say, a way to make the structure of the neural network, say, geometry aware somehow from a dense network to a sparse network, can exploit a sort of coarsening or refining a procedure as, say, in usual procedure for the sake of meshing, say, complex domains. So somehow we can, say, turn off, essentially imposing some sparsity constraints, we can turn off some weights in a dense layer if the two vertices in the, say, corresponding mesh are essentially far from each other. And for instance, in the solution of a small and simple problem, but if you compare the performance of a, say, of an architecture featuring a dense network or a mesh-informed network, you can easily see that the, say, memory consumption is much lighter, and also the errors can be further decreased. So we have architectures that are even easier to train, that allows us better generalization capabilities, and that are also lighter. Somehow we can inject information about the geometry in all this. Now there are two more parts that are, of course, much faster than the previous ones. A second task is related with forecasting and model discovery. Remember, so far, time entered as an additional parameter in the, say, in the DL-ROM or in the POD DL-ROM construction. Why not to exploit LSTMs? Somehow we have time series related with, say, snapshots of the solution over time. So first, we have tried to simply replace the convolutional autoencoder of before with an LSTM autoencoder without, say, doing anything else. But this is not sufficient to, say, perform better generalization capabilities of those networks for time-dependent problems. What we, say, did has been to couple, say, a parameter POD LSTM ROM with a time POD LSTM ROM, because we may be also interested to, say, get the solution of a given system not just for new unseen parameter values, but also for, say, future times compared to the training window where we have collected data. So this boils down to a sequence-to-sequence learning problem that you for sure know better than me, for which, say, predicting the solution for new parameter instances, say, at future times can be tackled by a sort of two-step processes exploiting LSTM. Somehow we need to generalize with respect to the parameters, but also with respect to time. So first, we try to predict what happens with a new parameter instance by, say, modifying a little bit, say, the architecture we have there so far, and then, say, we want to advance in time, say, in the future with respect to the final time where we collected training data by performing a sort of time series prediction by means of LSTMs. And all predictions in this stage are now performing the reduced dimension. Results. This is an advection diffusion equation. You have a source that can be, say, placed everywhere in the domain, and then you have a convective effect because you have, say, this rotation. Those are results related with a testing window that in time is still, say, equal as the training window, but what is changing now are just the parameter instances. We want to solve the problem for new scenarios. Adding LSTMs already allows us, say, to perform, say, slightly faster predictions. What is indeed useful, this kind of LSTM architectures too, in this case, is to perform, say, time extrapolation. Somehow we have say, a testing time window that now is, say, featuring 40 more time steps. So this is the future compared to the window where we collected data. And this is, say, the evolution of the relative error. So even if we are predicting, if we are forecasting the solution in the future compared to the, say, window we explored during the training, well, the error is still, say, under any desired threshold, I would say. And this is what happens in the case, say, of a much longer testing time window. You may ask yourself, well, here the problem is somehow periodic. These features, say, a good periodic behavior. But this also this is the case of fluid dynamics, the same problem as before, where we are able to generalize slightly less than before for new, scenarios. This is what happens for aperiodic systems. And this is an already low-dimensional system. This is a prey-predator system with 3 species interacting with each other, so a Lotka-Volterra-like system. So we have no need here of performing any kind of reduction through POD or whatever. Well, here what happens is that for, say, different parameter values, you experience a different kind of patterns in the orbits of this dynamical system. And also in this case, well, the error, in any case, is not, say, exceeding, say, any desired threshold for testing times that are larger. Which is the outlook in this respect? Well, a more general perspective is related with a more, say, general way to frame this system identification. So somehow we have to play with dimensionality reduction, but with the identification of a dynamical system behind. So far, we were not interested to obtain an explicit, say, form of the dynamics, at least in the rating space. But we could do this. And the kind of techniques we are going to, say, couple with the autoencoders as before is the so-called sparse identification of nonlinear dynamics. This is just one of possible, say, techniques that can be used to, say, perform this kind of task. A couple of words on this. This is nothing but a sparse linear regression problem over a dictionary of functions. The requirement is that, say, we need to rely on full state observations, and this is not always the case, of course. This is typically used for low-dimensional dynamical systems. Branton and Kurtz that introduced these 5 years ago, 6 years ago, at the beginning, say, dealt with, say, very low-dimensional systems, penduli, or, say, very simple mechanical, say, problems. The idea of coupling, say, autoencoders to, say, perform dimensionality reduction and SIMD is not ours, but what we have done essentially is to generalize this to the parameter-dependent setting, where you are interested to perform this combined reduction identification in multiple scenarios. So this is nothing but a linear, a linear combination of functions that can become possibly nonlinear. This is, of course, a strong requirement. You still need to prescribe this dictionary of functions that you want to combine, and then the sparse regression will, say, enable to identify the coefficients to be chosen. This is somehow the global picture. Somehow we are trying to discover which is the latent system that, say, regulates the dynamics of the system at the latent dimension, dealing with, say, the parameter-dependent case. You can, say, perform, say, the minimization of a loss that features, say, compatibility of the data, of the time derivatives of those data, and also, say, imposing some sparsity and some constraints on this kind of system. And this is a paper that has been very recently submitted, and these are some results, for instance, in the benchmark cases before. For the sake of time marching, we want to somehow learn the dynamics to be able to integrate the dynamical system, say, on longer time intervals, and then, of course, to, say, to reconstruct the solutions, but also to perform continuation if you want to somehow discover which is the behavior of this kind of systems when parameters, for instance, introduce bifurcations or transitions. This is the case of the transition from laminar to unsteady from the flow past a cylinder, and correctly this is identified at the critical Reynolds that literature gives us. Last but not least, what to do if you have data coming from different models. How to combine data coming from, I don't know, discretizations computed on different meshes, or featuring different time steps, or whatever. Well, neural networks can also in this case provide a possible solution. We can, say, approximate the high fidelity output. This is, for the time being, related with, say, some output quantities of interest, and I will give a couple of examples in this respect. Leveraging few data from the high fidelity model, very usually say the high fidelity model is very expensive to be solved, and you have very few data regarding this high fidelity model, but you can rely on many low fidelity models themselves. They would say not be useful because maybe the low fidelity model is too poor, is too bad. But leveraging, say, the informations brought by those two different sources, by those two different models, is indeed a possible idea. How to combine the information together? These are three possible, say, strategies. Well, either training a network that, say, combines everything together, we can say, modeling directly the desired function, the high fidelity model, by considering the low fidelity output as a sort of intermediate latent variables, or doing what we have called two-step procedure. Somehow we want first to learn, say, the low fidelity function and predict their values at the training inputs of the high fidelity data. And then somehow try to learn the correction, what somehow allows us to bring, say, low fidelity into high fidelity data. Somehow splitting this task into different subtasks, and even more in three different subtasks with a three-step architecture where this, say, this, say, lean block is, say, taking care of learning, say, which are the linear correlations between the high fidelity and the low fidelity data sets, just leaving to this final block what is not, say, included in this main portion. Example, this is a problem in acoustics. This was also, say, to span the different applications coming from different fields. This is a two-dimensional, say, Helmholtz problem. You have four parameters that tune the shape of this acoustic horn, and then you have, say, the frequency. And we want to compute the index of reflection intensity to measure some of the transmission efficiency of these objects. We have two models. We have finite elements. This is the high fidelity model. And then we play with a very bad reduced order model. So a reduced basis approximation like the ones seen at the beginning, but including very few basis functions, something that, say, itself would be very useless because too poor, say, too bad. Well, these are the results. By changing the number of basis functions in the low fidelity model, so better and better low fidelity model from top to bottom, and more or less high fidelity data. Very few high fidelity data, 8 or 16 evaluations of that output. Something that, say, is reported here, say, tell us that if the reduced basis model features 5 or 10 bases, compared to the black one, that the black is the high fidelity, well, it is an extremely poor low fidelity model. Nevertheless, even if I have a bad low fidelity models like those, combined with few high fidelity data, well, the output say can be correctly reproduced, and in particular now results are quite small on the screen, but say those two steps or three steps architectures are indeed better than the intermediate option to perform this kind of reconstructions. This has been also recently, a couple of weeks ago, this paper has been accepted on CMAME to the time-dependent case where, say, data are actually time series. Well, applying the structure of before to time series was actually, say, useless. We injected also in this case LSTM networks to, say, generalize the three kind of architectures that I have introduced before, just to, say, see that if low fidelity only are used, this is once again a lockable Terra system for the sake of dimension. So what happens if you have low fidelity data over the whole, say, time range? Well, things are bad because the low fidelity model is bad, and then you have this shift. What happens if you have high fidelity data but just until a certain time? Well, in the future the prediction is totally bad. Well, leveraging high fidelity data till this time and low fidelity data till, say, a much longer time interval allows us at the very end to get a good prediction for new, say, scenarios. And this is what happens, for instance, also in the case of the lift coefficients. Once again, this is the flow past a cylinder. This is in time for different Reynolds, the behavior of this, say, output. Well, the high fidelity is better than the low fidelity. These are the, errors between, different options. Well, if you only rely on low fidelity models, well, things are bad. But also if you rely on, say, a pure feed-forward neural networks trained on few high fidelity data. So you need to rely on LSTMs. But if you are just on a single fidelity, even if you are injecting LSTMs, well, the situation is not very good. Situation is not good if you rely on a multi-fidelity framework without LSTMs. This is the case. Well, situation, increases substantially if you combine information from different models, including LSTMs in the case of time series. And this is what happens now. This is a very quick outlook. If you want to perform all this story on the solution approximation, well, you can do this by performing, this sort of, LSTM multi-fidelity neural network regression on, for instance, POD coefficient. So we come back to the point where we started from. If we project all the data, for instance, obtained with simulations on different meshes onto a POD space, well, we can learn in the future which is the behavior of the POD modes, and then, perform a multi-fidelity simulations that resembles quite closely the high fidelity one. This was the last result, and this is the last slide about perspective. So the aspects I covered, I hope, have somehow captured your interest and your curiosity. Well, somehow deep learning allows to enhance and resolve the models. We want really to combine aspects and tools from, classical scientific computing and numerical analysis and deep learning. This is, for the time being, somehow the picture, which could be, future directions to, further enhance. Well, an aspect, for instance, is related with the inclusion of physical constraints into the DL-ROMs architectures. So far, there are no physics, in the, process of generating the approximation. We would like maybe to make all this adaptive. We would maybe to perform multi-fidelity approximation of outputs, adding uncertainty or assimilating data on the fly, because this can be another situation of interest. And regarding forecast, well, we would like to, extend what we have done so far to, partial or noisy data, or maybe also trying to learn the dictionary from data. And I think that some of these aspects somehow crosses, current, developments that many of you are focusing at the moment. The final goal is once again trying to do, to go beyond the direct numerical simulation in the direction of the uncertainty quantification, the optimal control, and the model learning. So sorry for having been a bit late. This is a list of references, and this is, our key of Polytechnic. Thank you.
Thank you, Andrea. Personally, I find really very interesting this kind of use of learning. It was completely unexpected to me until I discovered 1 year ago. So, there is any question for Andrea?
I have just a small question because I didn't really get this point. When you were discussing the speed up of DL-ROM with respect to numerical simulation, were you considering the time for, let's say, training the neural network, or the inference part? Okay, so you were comparing the full numerical simulation on one side against the inference.
Yeah, for a new scenario, for a new, parameter value, take this case. Here I am, of course, spending less than an hour to train all my network. And this allows me to get, solutions of the flow for a new Reynolds number in 0.1 second.
Okay.
For
While
new
on the
Reynolds.
other hand, you have to run the numerical simulation.
This is the case, for instance, here. Here you train everything in about 1 hour, and then you get solutions in less than a second. Of course, the dimension of the original problem has a clear impact on the training times. On the other hand, this is not the same impact on the testing time, because as soon as the dimension, say the latent scale and the latent level is very small, well, I tend to really get very, very fast insights.
Okay.
I was wondering, I didn't really get when you were talking about SIMD without encoders and parameter dependence.
Yeah.
What is the interplay between the two? Do you condition the latent representation in the autoencoder, or do you just like I didn't really get it?
I reach the slide, I reach the point. This one. Somehow all what is B here are parameters. Somehow you get, for instance, a representation now under a dictionary that is independent of the parameters, but with a representation that in the same spirit of a reducible model is dependent for instance.
Okay, so basically there is no conditioning of the latent representation by the parameter directly. It just goes into the library dependence.
Yeah, for the time being.
Have you considered maybe
For the time being, no, but this is a very interesting point indeed.
okay.
Another point related to this is, of course, the knowledge of this dictionary here is assumed to be, say, the same since the beginning. But of course, this can also be, say, somehow adapted or, say, learned on the fly. Yeah.
Okay, guys. There is, as the previous times, there is an hierarchy in the whole of the department. We need the department to come back, and you can discuss with Andrea and with other guys.
There are also, I mean, Stefania is actually one, say, the main engine behind, say, most part of this, so you can also address questions, say, to her. Paolo as well, Paolo that is, say, a professor at Knox also, say, was a key player in this, so you can also address questions. Thank you.